Assalamu alaikum. Dear students, in the previous lecture, we have discussed about the high frequency eddy current heating and its advantages. After this, we will move towards the electric arc heating, and after this, we have moved towards the arc furnaces, which includes the direct arc furnace and the indirect arc furnace. And in the last, we have discussed on the methods of obtaining power supply from arc furnaces. So from today, we will start our discussion from another type of heating, which is named as dielectric heating. Whenever there is a non-metallic parts such as wood, plastic, bone, ceramics are subjected to an alternating electrostatic field, dielectric loss occurs. These losses are used in dielectric heating, which appears in the form of heat. In the previous types of heating, we are going to heat or melt the metallic parts, wherein we just sprinkle the high resistance powder on that particular material, and then we will heat or melt that particular material. But dielectric heating is used to heat up the non-metallic parts, some of named as before. The material to be heated is placed as a slab between two metallic electrodes across which high frequency voltage is applied. From this sentence, we can easily judge that what is the basic methodology behind the dielectric heating. Here, the authors explained that there are two metallic electrodes. So, we already know that in the configuration of capacitor, we have two metal plates, one above, one below, and between which there is some dielectric material. So the phenomena behind the dielectric heating is same, that there are two metallic electrodes and between which we have placed the material to be heated, and these metallic electrodes are supplied with a high frequency voltage. To ensure sufficient loss and to give an adequate amount of heating, frequencies between 10 to 30 megacycles per second must be used, and the voltage needed may be as high as 20 kV. Here the basic requirement of frequency and voltage is given in order to get the adequate heating. The necessary high frequency supply voltage is obtained from a valve oscillator. How can we adjust the frequency? By using a valve oscillator. The current drawn by the capacitor when an AC supply voltage is applied across its place does not lead the supply voltage by 90 degrees exactly. In ideal case, there is the difference, there is the phase angle between the current and voltage is 90 degrees. But in practical scenario, it is not 90 degrees because of the material which is present as a dielectric material. Due to this component of current, heat is always produced in dielectric material placed in between the two plates of a capacitor. Because whenever we place the dielectric material between the two metal plates, there is some phase difference occur between the voltage and the current. And this phase difference is basically represented in the form of heat, which is going to be delivered to the dielectric material which is to be heated. Figure 3.19 basically representing the phenomena of the dielectric heating, where there is two metal plates, one above and one below, just like the capacitor configuration, and between which there is some material or charge which is to be heated, and these plates are supplied from the high voltage frequency supply. The electric energy dissipated in the form of heat energy in the dielectric material is known as dielectric loss. The dielectric loss is directly proportional to the frequency of the AC supply. This method of heating is also employed for drying of textiles, manufacture of plywood or paper. The overall efficiency in case of dielectric heating is about 50%. In insulators or non-conducting materials, the amount of heat produced by dielectric heating can be calculated as follows. From the figure 3.20, there is a circuit diagram where there is a capacitor or the resistor which are in parallel, and the high voltage frequency supply is represented by V. Here R is basically representing uh, the characteristic of the material, because in capacitor, if C is ideal, then the phase difference between the V and I is 90 degree. Since the dielectric material has its own characteristic, so there exists some delay between the V and I, which is represented in this figure as R. So we can say that the total amount of current is divided into two parts. One is the capacitive current and one is the resistive current. So the phasor representation of this figure is shown in V, where the horizontal axis there is the voltage V, and at the vertical axis there is a capacitor current IC. If the capacitor or the dielectric material is considered ideal, then we can say that the phase difference between the IC and V is 90 degree. But since there is some R, so that's why the amount of current phase or lags behind the IC by an angle phi due to the presence of IR. The material to be heated may be considered imperfect dielectric of a condenser and may be therefore represented as a capacitance placed in parallel with a resistor as shown in figure 3.20a. The phase difference of the circuit is shown in figure 3.20b. If V is the supply voltage, F is the frequency in Hertz, cos of I is the power factor of the load, and C is the capacitance of the condenser in farads, then we can say that the capacitance is C, which is equal to epsilon naught multiplied by epsilon R multiplied by A divided by D. Now epsilon naught is the permittivity of the vacuum and its value is 8.854 multiplied by 10 raised to power minus 12 farad per meter. Epsilon R is the relative permittivity of the dielectric constant. Here we can say that it is based on the material to be heated. A is the surface area of the electrode and D is the spacing between the electrodes in meter. Now how much is current is flowing through the capacitor is given by IC, which is equal to V divided by XC. XC is equal to 1 divided by 2 pi FC. Here there is some mistake, 1 divided by 2 pi FC. So the overall amount of current is 2 pi FCV amperes. Now how much is the current drawn from the supply is I, which is equal to IC, which is equal to 2 pi FCV. Now the power produced is P, which is equal to VI cos of phi. We just put the value of I over here, which is equal to V multiplied by 2 pi FCV multiplied by cos of phi. By simplifying it, we can say that P is equal to 2 pi FCV square, and the voltage is obtained from this equation, which is represented by this. So by using these formulas, we can determine the value of the voltage or the power produced or the voltage required. We can also, by using these formulas, we can calculate the value of capacitance of the insulating material and how much is the voltage or power is required to heat the dielectric material. Now, what are the advantages of dielectric heating? Since the heat is produced throughout the whole mass of material, we get uniform heating. By conventional method of heating, it is not possible to achieve. Short time is required to complete the process as compared to the other methods. Materials heated by this method are non-conducting, so by other method, heat cannot be conducted to inside so easily. Now, what are the disadvantages of dielectric heating? Only those materials can be heated which have high dielectric loss. The cost of equipment required for dielectric heating is so high that it is employed only where other methods are impracticable. Now we will move towards the application of dielectric heating. It is used in drying tobacco, paper, wood, gluing and bonding of wood, welding of PVC, sterilization of medical supplies, for producing artificial fibers, heating of bones and tissues, and food processing. Now students try to solve example 3.4, which is based on the formulas which we have derived or discussed in the previous section. Now we will move towards another form of heating, which is the infrared heating and its relevant applications. Infrared heating is suitable for low and medium temperatures. In this method of heating, heating element consists of tungsten filament lamp operating 250 and 1000 watt. The lamps are operated at 115 volt. The filament of the lamp are operated at 2300 degrees Celsius instead of 3000 degrees Celsius, giving greater proportion of infrared radiations, and a longer life reflectors are also used with lamp to direct whole of the heat emitted to the charge. This phenomena is also used by therapists in order to supply the heat to the frozen muscles of the human body. The plant sizes ranges from a single lamp to chambers containing several hundred of kW of lamps. With this method, temperature between 200 degrees Celsius to 300 degrees Celsius can be obtained. For obtaining best results, the infrared lamps should be located at a distance of 25 to 30 centimeters from the object to be heated. It is also called radiant heating. Now, what are the advantages of infrared heating? That by this heating method, we can do the rapid heating. Its compactness of heating unit, it is more flexible, more safe than other types of heating. Now, the application of infrared heating, apart from the medical side, that by this infrared heating, we can dry the painted surface. We can dry the radio cabinets and wood furniture, the drying of foundry molds, preheating of plastics prior to molding, drying of pottery, paper textile, where moisture contents is not large, drying of enamel on enameled copper wire. After this, we will move towards the last method of heating, which is the microwave heating. Microwave technology uses electromagnetic waves that pass through the material and cause its molecule to oscillate, generating heat. So microwave ovens are available at every home, and it works on the principle of microwave heating. In conventional heating, the heating The material surface heats first and then the heat moves inward. However, in microwave heating, heat is generated within the material and it heats the entire volume at about the same rate. Industrial microwave furnaces have traditionally used fixed frequency electromagnetic waves that can cause uneven heat distribution. New technology varies the frequency, eliminating hot and cold spots. Microwave technology can be combined with conventional heating and drying units and is easily automated. The microwave heating is frequently used in microwave ovens for efficiently and uniformly heating and drying. Examples of microwave heating is micro oven. The advantages include energy required as compared to conventional heating is less 10 to 30% for fuel-fired process. Rapid and even heating. It requires 20 to 30% less floor space than conventional units. It can be instant on and off. You can also dry the material at low temperatures. Additional cost saving come from better production speed, waste reduction, and product quality. The disadvantages include it is a costly process, more chances of failure, lack of technology awareness, risk of accident, unhealthy for human being. And its used is in food processing, rapid wood drying, paper making, polymer and epoxy drying, and textile drying. Now we will move towards the most important part of this chapter, which is the design of heating element. The wire employed for heating element may be circular or rectangular like the ribbon. Knowing the electrical input and its voltage, the size and length of wire required as the heating element to produce the given temperature can be calculated. So here he is giving us the hint that we know the electrical input and its voltage. Now what our target is, we have to determine the width or size and length of the wire, length of the heating element in order to get the desired temperature. The temperature of the heating element at the initial stage will increase gradually, and after some times it attains the constant temperature. At this instant, the heat dissipated from the surface of the element is equal to the input of electrical energy. Now here he has given again the hint that how can we calculate the input of electrical energy. How can we calculate? By this, the heat dissipated from the surface of the element. So what we have to calculate? We have to calculate the heat dissipation from the surface of the heating element. Then that becomes the input of the electrical energy. The temperature will be sufficiently high to assume that heat is dissipated by radiation. Now heat dissipation according to the Stephen's law is given by this equation. In terms of watt per centimeter square, we can use this formula, and in terms of watt per centimeter per meter square, we have this formula. Now the electrical power input is given by P, which is equal to V square by R, where V is the supply voltage and R is the resistance of heating elements. Now we put the value of R, which is equal to rho L divided by A. So the denominator of denominator becomes the numerator over here, which is equal to V square multiplied by A divided by rho L. Now what will be the value of A? A is basically the cross-sectional area. So the value of A is replaced by pi d square divided by 4. So in simple word, we can say that the A is pi r square and r is equal to d by 2. The square of d by 2 is d square by 4. So we'll put the value of A over here and we get the value of the electrical power input in this form, which is equal to pi multiplied by d square multiplied by v square whole divided by 4 rho L, where rho is the specific resistance of the wire material, L is the length of the wire, and d is the diameter of the circular wire. Now the surface area of heating element is pi dl. So the heat input per centimeter square of surface area is pi d square v square divided by 4 rho L, since we are going to calculate the value of heat input per centimeter square. So per surface area of the element is 1 divided by pi dl. By simplifying this, we can get the value of v square d divided by 4 rho L square. Since we have already show that the heat dissipation is equal to the heat input, so by equating equations 1 and 2, we get that heat dissipation is equal to v square d divided by 4 rho L square, or we can say that d by L square, which is equal to 4 h rho divided by v square. We also know that E is equal to v square by r and r is equal to rho L over A. So from here we can simplify it by v square by p, which is equal to r, and r is equal to rho L over A, and in A, in place of A, we put the pi r square, which is equal to pi by 4d square. By simplifying this, we can get this equation, which is represented by equation 4. So by solving the equation 3 and equation 4, we can get the length and diameter of the wire, which can be calculated easily. In example 3.5, the author has calculated the value of D and L on the basis of these derivations which we have discussed in the design of heating element portion. So try to solve it by yourself. Now we will move towards the last topic, which is the causes of failure of heating element. The main causes of failure of heating elements are given: formation of hot spots, and the second one is the contamination and corrosion. Hot spots are the points in the heating element which are formed at high temperature. One of the reasons of formation of hot spot in heating element is high rate of local oxidation that may reduce the element cross section, thereby increasing the resistance at that spot and produces more heat locally and causing breakdown of element. The other causes are wrong fused material may result in sagging and wrapping of the material. The second one is the contamination and corrosion. Gases of the controlled atmosphere prevailing in the annealing furnace or fumes from the flux used in brazing furnaces or oil fumes caused by heat treatment of components contaminated with lubricant contaminate the elements and produce dry corrosion. So we already discussed in our initial lectures that how can we avoid the failure of heating elements and how can we improve the efficiency of the heating element. So for today it's enough. and if you feel any confusion during today's lecture, you can discuss with me during the discussion hour. So with the today's topic, this is the end of the electric heating chapter. Briefly, we can say that in today's lecture, we have discussed about the dielectric heating, its advantages and disadvantages. After this, we will move towards the infrared heating and its application and microwave heating. After this, we will move towards the design of heating element and what are the possible causes of failure of heating element. From the next week, we will start our discussion on the electric building. So for today, it's enough. Thank you very much and Allah Hafiz.